if everything works properly. Okay. Okay. Does it work, Roberto? Can you hear me?
Yes,
it works.
Okay, it works. So,
Yes.
okay, well, let us start. First of all, thank you very much for your kind words of introduction, and thank you very much to all of you who participate in this colloquium. And let me introduce what I want to say. I mean, it's just a very, let me say, rather pedagogical introduction to what has been done over the last few decades in turbulence, and my focus will be essentially on homogeneous and isotropic fully developed turbulence. I mean, this is a, so to speak, somehow a narrow view with respect to many problems that you have in turbulence. And in fact, I am within the kind of people that doesn't believe that there is a just unique problem concerning turbulence. Now, our starting point, even in this narrow view, of course, is that we consider a simple Newtonian incompressible fluid, which is described by the Navier-Stokes equation. Now, the Navier-Stokes equations are extremely well supported by experimental data, and the only phenomenological part is the one concerning the viscosity, which anyway is extremely well fitted by experiments. So I would start by assuming that the Navier-Stokes equation describes extremely well what we call the turbulent motion of an incompressible and simple Newtonian fluid. Of course, there are many other kinds of fluids where you have to do some work, and the Navier-Stokes, as it is formulated in this slide, doesn't work. So, just to introduce the subject, we start by focusing on what we call the Reynolds number. Now, there are many ways to introduce the Reynolds number. The simplest way is to consider some kind of geometry, for instance, this kind of cylinder with a characteristic scale, and where the flow is going around with some velocity u, and the Reynolds number is can be defined, as I said, in many different ways, but what I like to say is that the Reynolds number is the ratio between the time, the characteristic time for the viscosity to act in the system, which goes like L squared over nu, divided by the time scale, which corresponds to the acceleration time due to inertial effect. So it's the time scale that you need to cross, let's say, these sides at the velocity u. When the viscosity is not dominating the system, then what happens is that the time scale becomes extremely large, and the Reynolds number, of course, becomes extremely large. As a matter of fact, when the Reynolds number changes, you can see from this simple cartoon, what happens is that the flow starts to be laminar, but when it increases enough, what you find is that the turbulence appears, and you have a really chaotic in time and space motion of the fluid. So, roughly speaking, just to fix the idea, if you take a car moving at 100 km per hour, which is roughly a standard velocity in a highway, then the Reynolds number is order 10 to the 7. So, what is the general question we want to address in this talk? And it concerns the statistical property of the velocity fluctuation when the Reynolds number is going to infinity. This is the region of high Reynolds number that we call fully developed turbulence. And there are, of course, also in this narrow view, there is also a number of different questions you can ask. So we will concern ourselves with one among the other questions, which is, do the statistical properties of velocity fluctuation depend on the forcing and mix and the dissipation effects? In other words, when we look at the system in homogeneous and isotropic turbulence in fully developed case, do we expect universality with respect to forcing and dissipation mechanism, or, I mean, something that depends on the forcing and dissipation should anyway shape the statistical properties of small-scale turbulence? Let us still remember that the only thing that we think it's phenomenological is just the dissipation mechanism. Now, within the few decades, what happened is that there was a really major role in the numerical simulation of turbulent flow. This is an old transparency, it's about 10 years old, but it tells you that in fact around 80 and 90 there was the ability for people start simulating Reynolds number of order 10 to the 4. I mean, this is a technical point relating the real Reynolds number to some other kind of number that is used in the numerical simulation. So it's here around 1990 there was already the ability to simulate turbulent flows at Rayleigh number 10 to the 4. And the situation is still improving, and now we are definitely able to simulate numerically Reynolds number of order 10 to the 7. And this implies that we are able to get from the computer simulation many informations that otherwise are extremely difficult to obtain from experiments. Although, of course, we compare all the situations that we found with the experiments as well. Now, start with the basic problem of turbulence. Now, what is called the zero law of turbulence, or if you wish, the viscous anomaly, is the most important information that must be kept in mind by dealing with turbulent flow. Namely, that what has been found experimentally and numerically and in many other circumstances, as I will discuss later on, is that the energy dissipation in a given situation, of course, by fixing the geometry or whatever is the forcing mechanism, well, the energy dissipation is independent, it goes independently from the Reynolds number. So when the Reynolds number increases, it goes to a constant. Now, since the Reynolds number is inversely proportional to the viscosity, by saying that the energy dissipation goes to a constant when the Reynolds number increases, it's equivalent to say that the gradient of the velocity field must go like the square root of the Reynolds number, so it becomes extremely large. Now, this is not a trivial statement. For instance, it's not true in two-dimensional turbulence, where in fact energy dissipation is not it is not a constant with the Reynolds number. But I will not discuss about this. I mean, it is a non-trivial statement which has been one of the starting point in developing any statistical theory of turbulence. And in fact, as we shall see, it's the starting point of the famous Kolmogorov theory. According to this rule, what we observe that the field theory described by the Navier-Stokes equation for turbulence is probably is the only one field theory which generates its own ultraviolet divergence. You don't need any noise or external kind of fluctuations to have large gradients. The gradients becomes large because of internal dynamics of the system. And this is something that we need to explain, or we need to put as a fundamental requirement in any kind of theoretical and as well as in experimental investigation. To start understanding this feature, let me recall, at least historically, one of the first evidence of this viscous anomaly, the fact that the energy dissipation goes to constant when the Reynolds number goes to infinity. And it's the famous Richardson diffusion, which was, conjecture and somehow proved, at least experimentally, by Richardson in a famous paper in 1926. So what Richardson did was to consider the probability, I mean, what it was investigating was the diffusions of something in the atmospheric turbulence. And so instead of looking at the concentration of a scalar, which was what people did at the beginning of the last century, what he looked was at the probability of PR of two particles to be at a distance r after some time. And then he was able to derive from the experimental observation that such probability must satisfy this diffusion equation, which is in a rather different form from the classical diffusion equation. And he noted, by looking carefully at the experimental data, that the diffusion term was dependent on R. And this is a very, very characteristic features of all turbulent flow, where what we call the effective diffusivity or the turbulent diffusion is not a constant, but depends on the scale at which you are considering the system. As a side product of this observation is, of course, that if you look at the square, at the average of the distance square between these two particles as they are advected by a turbulent flow, what you obtain is an equation like this. I mean, the average of the distance square goes like r to the 4/3. Now, what are the consequences of these observations, which was mostly underlooked at the time of Richardson? Well, one of the consequences is the following. Suppose that you take two particles at the distance r, and then you consider the, roughly speaking, the velocity at which the two particles can separate. Well, this separation in time is proportional to, of course, to the difference in the velocity. So, in average, you have the possibility to say that what Richardson found with this r to the 4/3 square was an indirect measure of the product, statistically speaking, between the velocity difference and r. Now, for this quantity to scale as r to the 4/3, what one immediately reach is that for large Reynolds number, the velocity difference in a turbulent flow must go like r to the 1/3. And this implies that the velocity field is rough. I mean, it's not Lipschitz continuous, it's Holder continuous. And one consequence, which was put forward only recently, is that in fact, when you have a velocity field which is rough in the sense of Richardson, then what you have, and here is the point, is the breakdown of the Lagrangian trajectories. Now, this is a peculiar feature of turbulence in the limit of infinite Reynolds number that is worthwhile to keep in mind. If you solve this equation, you immediately get that the separation between the two particles in time grows as a function of time, even if the distance between these two particles is 0. So what happens is that whether the time goes in one way or in another, it doesn't matter. What you have is that two coincident particles will separate at a finite difference, even if they are at initial this time in the same location. This is called the breakdown of Lagrangian trajectory. Now, as you can imagine, whatever property can the particle carry, momentum or more physically some particular characteristic like a scalar, then if you go back in time, what you observe is that the difference between the property of two particles separated at distance r will become closer and closer, and so will increase the gradient when you look at the system in the Euler framework. Therefore, two particle, this breakdown of Lagrangian trajectory is somehow linked in a way that we still have to clearly specify to what is called the anomalous viscosity, or if you wish, the viscous anomaly, or if you wish, the zero law for turbulence. An interesting historical remark about Richardson is that when he wrote this paper in 1926, in the introduction, he wrote also another paragraph with the title, Does the Wind Possess a Velocity? So he was very aware of the fact that this law was introducing a velocity field which was indeed rough. So in some sense, his intuition was correct concerning the peculiar features of turbulent diffusions in a system. Now, 20 years almost after Richardson diffusions, Kolmogorov made his breakthrough in understanding one of the most important properties of turbulence. He started with the case of homogeneous and isotropic turbulence, and first of all, he introduced a quantity which will play a fundamental role in the rest of my talk, which is the velocity difference between two particles, and in particular not all the possible velocity components, but the one which are in the direction of the distance separating the two particles, so the longitudinal part of the velocity difference. And he showed that that quantity was the only one which characterized the full statistical property of the system if we assume that the system is homogeneous and isotropic. Then he derived, starting from the Navier-Stokes equation with the viscosity, he derived an exact formulation of the statistical property, at least for one of the many order moments that you can build up with this quantity, which is the famous 4-fifth equation. Now, this equation is crucial because it contains several things. One is this term, which is the third order moment of the velocity difference. Now, this term, after a long, somehow painful derivation, can be shown to be proportional to the amount, to the rate of energy transfer from the large to small scale. So whenever this quantity here is negative, then you can immediately argue that there is an energy transfer from larger to smaller scale. And this is a quantity which is due to the transport, nonlinear transport of the velocity field, as well as this term, which is related to the average rate of energy dissipation in the system. Now, the crucial contribution of Kolmogorov was not only to obtain this exact equation, but to state for the very first time that the energy dissipation should be considered independent of the Reynolds number when the Reynolds number goes to infinity. Up to Kolmogorov, that statement was almost behind the mind of many people, like Prandtl, by Richardson himself, or by von Karman. But Kolmogorov was the first to make this statement. So when you are at very large Reynolds numbers, this quantity is finite, this quantity is finite, this can be discarded because the viscosity effect, so it's proportional to 1 over Reynolds number, and so you reach the conclusion that when the Reynolds number is large, you should observe a scaling law like this, with a third order moment of the velocity difference proportional to r and the minus sign here. Then you can go on. At this time, you can leave exact information, and you say, okay, if this is true, then we may think that the probability difference, the probability of the statistical fluctuations in turbulence can depend only on the energy dissipation and the distance r, and therefore you can argue that in general, you observe a velocity difference which is proportional to r to the 1/3. And now you see that, in fact, Kolmogorov was able to derive, so to speak, the Richardson diffusions from his argument. So the Kolmogorov theory was really a moment where different ideas built up over the 40 years of work at the beginning of the last century was put together in a framework that was specifying almost very well this property of turbulence, at least in homogeneous and isotropic case, and for very large Reynolds number. Another consequence of turbulence of the Kolmogorov theory is the introduction of a characteristic scale, which is the Kolmogorov scale, here defined by eta, okay, which is obtained as the balance between the viscous effect and the Kolmogorov equation at very small r. And you see that eta is proportional to the Reynolds to the minus 3/4. So it means that the effect of turbulence will make the velocity field to fluctuate at extremely small scale. Just to give you an order of magnitude, if you consider a cylinder of 1 meter diameter, which is, and the velocity field which is flowing with a 1 meter second, then a rough estimate of the dissipation scale is order 1 millimeter, and associated with this case there is a characteristic time of this fluctuation, which is simply given by the dissipation scale divided by the fluctuation at that scale, which is order 1 millisecond. So you see that at very large Reynolds number, fluctuations can be observed almost everywhere, and this is an important application in all fields of turbulence, not to consider the theoretical one. Another follow-on of the Kolmogorov theory is that if you take the scaling law of the prediction by Kolmogorov, then you obtain an energy spectrum. I mean, you compute the energy. You can predict what is the characteristic shape of the energy spectrum for the velocity fluctuations, and the velocity fluctuation must show an energy spectrum which goes like k to the minus 5/3. Now let me open a small parenthesis. Most of the people think that the Kolmogorov theory was the prediction of the energy spectrum. In fact, this is not true. The energy spectrum goes like k to the minus 5/3 if you assume the scaling of the velocity field as in the previous slides, I mean, like r to the 1/3. Now, the real prediction of Kolmogorov was this exact equation, and if you want to know if the field is look like a Kolmogorov turbulence or not, you have to compute only the disturbed structure function. Okay? Now, so to summarize the Kolmogorov theory, we have an exact statement, we have some forcing which generate turbulence at very large scale, then there's something which happens in the system by transporting energy from large to small scale, and then you have dissipation. And of course, the Kolmogorov conjecture is that the probability distribution of fluctuations will depend only on the rate of energy dissipation and the distance between particles. Now, next step, let us see what happens to this prediction if you compare it against, for instance, one of the best numerical simulations done in the last few years. So you see that here are the results by Goto, Kaneda, and Ishihara in 2009. Now they are improved, and you see that the energy dissipation, in fact, is very well constant with respect to the Reynolds number. Remember, the Reynolds number is the square of this quantity. So here we are 10 to the 4. And the prediction of the Kolmogorov theory, which is the exact equation, which is this dashed line here, is extremely well verified in the numerical simulation as well as in the experiments. So the Kolmogorov theory, from the point of view of the two principal information, namely the third order structure function and the energy dissipation, is verified extremely well from the numerical simulation as well from the experiment. Now let's go to the next prediction of Kolmogorov. Now the next prediction is very simple. I mean, if the conjecture done by Kolmogorov is correct, then what we should observe that any moment of velocity difference to the any power p should go like p to r to the p over 3. And then if you make the ratio between any of this power with respect to S2, for instance, to the P over 2, this ratio should be constant for any value of R. Now, this is actually not true, and it was observed almost immediately after Kolmogorov put forward his theory, I mean in the 50s. And in fact, these are results from both numerical simulation and observations, where it is clearly observed that the prediction done by Kolmogorov conjecture, I mean, is a conjecture, not an exact statement, doesn't really work when you go from very large scale to very small scale. So this is from very large scale, which is this Gaussian shape like, to very small scale. And you see that the probability distribution change as a matter of fact. And this is the ratio of the fourth order moments of the velocity difference with respect to the second square. And you see that start from 3 when you have a Gaussian field is roughly equal to 3, and then an increase when you go down with the distance between the system. Now, of course, one starts to think what was wrong with the theory of Kolmogorov. Now, the theory of Kolmogorov was not completely wrong. As we said, it has something inside that has been proven to be correct. So the deviation from Kolmogorov theory are relatively small, and one can try to understand what was wrong with the original conjecture. The first thing that you can imagine is that instead of making that some trouble comes from this average. Now, of course, you can, within the Kolmogorov theory, you can think that the energy dissipation is not constant. In fact, the energy dissipation can be somehow related to the fluctuations over the large scale. So if the fluctuations over the large scales are roughly Gaussian, as it is observed in most experimental and numerical simulation, then you immediately get the probability distribution for the energy dissipation, which is extremely fluctuating. I mean, he has a probability of having small epsilon, which is much smaller than the probability to have the average value of epsilon, but it does not depend on the R. So in other words, I mean, if you think of the energy dissipation as one of the possible candidates that destroy the Kolmogorov conjecture, you are pointing in the only one direction, which is left by Kolmogorov, but the fluctuation of energy dissipation by themselves doesn't play a relevant role unless you do not introduce some kind of statistical or geometrical characteristic which depend on the distance r between two particles, or the velocity distance r between that you are looking at these measurements. Now, when you look at the velocity difference, what you look at is a fluctuation on scale r. So the problem is not just the fluctuation of the energy dissipation, but how they depend eventually in space. And in fact, we can try to understand this problem in a different way by looking, for instance, at the trajectory of a Lagrangian particle. Now, suppose that you take a particle, you put in the system this particle, and then the particle has the same density of the fluid, so it's a perfect tracer, and the particle will be advected by some velocity field. Now, knowing the trajectory or the velocity that is experienced by the particle, then you can, so to speak, predict its acceleration, because within the Kolmogorov approach, the acceleration is nothing else, nothing different from the velocity at the scale of dissipation, which is the smaller scale where the system can fluctuate with respect to the characteristic time for this fluctuation. Now, as we said before, we may have a reasonable estimate, or if you see, we can make a reasonable statement about the fluctuation of the energy dissipation within the Kolmogorov approach, and so you can make a prediction of the Kolmogorov theory on the acceleration experienced by this particle. As you can see here, there is this green line is what is obtained by the Kolmogorov theory, and the red dots correspond to the what is observed, in this case in the numerical simulation. So it is clear that the Kolmogorov theory is not valid when you go to very, very small scaling. Now, you can have a better look at this problem by looking really at the trajectory, and you see that if you look at the velocity experienced by this particle, the velocity is more or less fluctuating, okay? And then eventually you observe a very huge fluctuations up and down in the system. And if you now try to understand what is this fluctuation up and down, and you look at the trajectory in the three-dimensional space, you see that the trajectory in the three-dimensional space is going around a single filament. I mean, what happened, it's very clear. That what happened is that the particle sooner or later will encounter what is called a vortex, like a small cyclone inside the system. It enters this vortex tube, and it starts to rotate inside this vortex tube. So because of this rotation, you have a huge amount of fluctuations, and these huge rotations are not taken into account by the Kolmogorov theory. And by the way, you can see here that the acceleration in this numerical simulation, for instance, can be as big as 16,000 meters per second square. So it's really huge. So what is the conclusion of this first step? The conclusion is very clear. You can take three different points of view. The first one, which was taken by many people, was to say, okay, the turbulent field is characterized by very strong vortex filament, which eventually interact between themselves, and they are, so to speak, immersed in another kind of random sea of Kolmogorov-like fluctuations. This implies that, of course, in order to build up a theory for the turbulent fluctuation, you must know how the vortex tubes are created and dissipated, and it's very difficult to understand whether this property may eventually be, so to speak, independent from the dissipation mechanism or the forcing that you apply in the system. There was another point of view that was taken by other people that say, okay, the Kolmogorov theory is correct, but you cannot see the effect because you are at a relatively small Reynolds number. So all the things that you show us are somehow effect that you observe only in the relatively low Reynolds number limit. So asymptotically, everything will become like Kolmogorov. And then there was a third point of view, which is the one I will concentrate, that say, okay, let us assume that Kolmogorov was completely right, and in fact, that the scaling, that the rate, this quantity is the quantity, that the velocity difference is the quantity that we need to take into account in order to understand the statistical property of turbulence. And let's try to understand how we can generalize the Kolmogorov approach. Now, the idea was very simple, and afterwards it was, you get the idea. Before it was a mess, of course. And the idea was the following. You take the Navier-Stokes equation as they are, and then you look at the scale property of this equation. Namely, you make a transformation R in lambda, R view V, which goes like lambda to the H over V, so that all the other quantities which are dimensionally related scale properly. Okay, so time goes like lambda to 1 minus H, viscosity goes like 1 plus H, and so on. And then you see that if you put all these things together, the energy dissipation, which is the crucial quantity entering in the Navier-Stokes, in the Kolmogorov theory, goes like lambda to the 3H minus 1. So the basic idea is that, in fact, Kolmogorov selected H 1/3 as the correct scaling property for the energy dissipation to be independent of the Reynolds number. You can think of this scaling also as a scaling in the Reynolds number sense, if you wish. So the idea was, well, let's generalize this approach, but give a weight, okay, to this different value of H. And the weight to preserve scaling must be also a scaling function, which now depends of H in a different way. And it was assumed to depend in some way, as is reported here. Okay, and this idea was introduced by Parisian Frisch in the beginning of '80 and developed by other people, including myself, Paladin, Parisi, and Vulpiani. Now, the model is called the multifractal model. I mean, it's called the multifractal almost for historical reason. I mean, there is no reason to really think to some kind of fractal dimension, although it is can be considered a fractal dimension. Anyway, it's called the multifractal field. And in fact, what happened is that by this assumption, what you are really assuming that the energy dissipation, which is positive defined, is proportional to a multifractal measure. Okay. As soon as you have this idea, which is introducing a weight for any value of H, then of course what happens is that the limit of R going to 0, since the function d of H may eventually be nonlinear, it is believed to be a nonlinear function of H, then the property of SP is no longer dictated by H to the 1/3, but is dictated by some characteristic value of H, which minimizes this Legendre transform. Okay? And in fact, d of H has a well-defined property, is a convex function, and zeta p is a convex function as well. The only thing that we have to preserve, according to the Kolmogorov spirit, is the fact that the value of zeta 3 when p is equal to 3 must be equal to 1, so that the energy dissipation becomes independent of the Reynolds number. However, let me also point out that in this way we did make a theoretical statement about the statistical property of the velocity difference without really defining any theoretical model or any theoretical approach to compute d of H. The only thing that we introduce is that there is something similar to the entropy, if you wish, in a system, which dictate the fluctuations of the velocity field at very small value of R and for very large value of the velocity difference. Now, once you introduce this idea, then you have to care about a number of questions, which are in fact the question that was addressed and was addressed in the last 20, 30 years. Now, the very first question is whether or not there is anomalous scaling in the observed and the data. I mean, of course, scaling is a difficult problem, and you will see how we handle with this problem. Okay, the second point is whether this anomalous scaling is universal. After all, there is no reason why we should believe that this quantity, if are not dictated by the Kolmogorov approach, may not depend by some kind of forcing, by the way in which we force the system or by the way in which the energy may be dissipated. Then you remember the problem of the acceleration. Even if we are able to compute or to assume or to prove, at least experimentally, that there is an anomalous scaling, then how we can link the anomalous scaling with the statistical property in the very deep dissipation range. And then finally, how can we compute d of H or zeta p or whatever we want? I mean, the two things are related because zeta p is the Lagrangian transform of d of H, and of course, d of H is the inverse Lagrangian transform of zeta p. So the two quantities are clearly related, and we should give some hint on how to compute this statement. So let us start with the scaling. Now, the scaling, as I said, is a very difficult problem. I mean, it's a difficult problem in the sense that if you have a theory which predicts scaling, it also predicts usually what are the finite size effects. Now, in this case, the finite size effect depends on the Reynolds number. And even if you do experiments, you must really reach very large Reynolds number to have something which is, you may call a scaling. And if you want to understand whether scaling is anomalous or not, you must have a very good precision in order to make statement of error bars less than 2–3%. Okay? Now, here is just the situation that one finds in turbulence. I mean, if the Reynolds number is 10 to the 5, you see this square here, and I mean, you can obviously put a line between two squares, but no more than 2. I mean, you don't really observe any kind of scaling. Only when the Reynolds number becomes relatively large, very large, 10 to the 6, I mean, you observe something which you may call a scaling, but eventually, depending whether you do the fit here or there, the numbers that you get can be whatever you want. So the idea came true that in order to observe anomalous scaling, which is the point that we are looking at least when the Reynolds number is not extremely large, then the very simple thing that you can do is to look at any scaling quantity, assuming that this is a scaling quantity of r to the power p, as respect to r to the same quantity at the power p. So in other words, if you have anomalous scaling, you must see a difference between the scaling behavior of these two quantities. Now, in the case of turbulence, what we can do is to use the value of the third-order structure function. That is to say, the quantity that Kolmogorov was able to prove to be proportional to R in the limit of very large Reynolds number. Assuming that the finite size effects are relatively small with respect to this evaluation of anomaly, so I mean that the finite size effect in this quantity and the finite size effect in this quantity are, roughly speaking, of the same order of magnitude or the same order, at least when the Reynolds number is not too large, then you can immediately derive whether or not there is an anomalous scaling by looking at this relation, which is the one predicted by Kolmogorov. Now, you see here a case where you see the sixth-order structure function with respect to the third, and then the Kolmogorov prediction is this line here, which is 2, with a slope 2, and this is what you observe with the same experimental point that was used in this figure. So you see that now you can clearly observe deviation from what is the scaling predicted by Kolmogorov, and therefore, at least for these cases, you are able to compute the scaling property of the anomalous scaling property of turbulence with a precision which is enough to observe whether anomalous scaling is observed or not. In fact, what you end up, and this is a very short resume, is that the anomalous scaling is observed, and these are, for instance, the data for the sixth-order structure function, which with respect to the Kolmogorov theory is predicted to be 2, and now is much less than 2. And this is the value that is a function of the logarithmic of the Reynolds number, and according to this data, these are experimental data, the anomaly is there no matter what is the Reynolds number. So this rules out the possibility that the Reynolds number, when increasing the Reynolds number, sooner or later you will recover the turbulence, the Kolmogorov theory. And this is our present results that we have, putting together all the numbers that we know with the accuracy of 5 to 2%. And in fact, you see that the Kolmogorov prediction is clearly broken, and you observe an anomalous scaling in the system. In fact, there was an international work done by many people where there was an assessment about anomalous scaling, and that was done in 1994, so many years ago, where for the first time we decided that it was very clear two things. One, that the scaling was observed and that the scaling was anomalous. So this was somehow a little breakthrough in the sense that we start from discussing different theories which were not well based on experimental information, and we concentrated on why such an anomalous scaling should be observed. Exactly more or less at the same time, a real breakthrough from the theoretical point of view came into the field, and this was due to Robert Krikland. Now let me roughly describe you what was the Krikland merit. First of all, the big idea was to consider a passive scalar. Now, a passive scalar is something which is transported, like the temperature here, by a velocity and eventually dissipated by some diffusivity. Now, the velocity is supposed to be turbulent, but Krikland has the bright idea to consider not real turbulence, but to consider a kind of rough, so to speak, field that he make a model as a velocity random field which is delta correlated in time, which is crucial, and with a space correlation which is supposed to be r to the c. Okay, so if you think that the space correlation of the velocity field, so this implies that roughly speaking, the roughness of the velocity field goes like r to the c over 2. So for c equal to 2, the system is smooth, so the velocity field is smooth, and the roughness increase up to c equal to 0. Then, because of this strong simplification and because of the roughness, one can imagine that something can be said. That was the Krikland intuition. And in fact, one can derive from this equation and the assumption that the field is randomly correlated, a closed equation for the moments here of the temperature fluctuations to the power 2n. Obviously, all the moments of power negative of the powers goes to 0. And then we can derive this equation, and we could try to understand whether this equation shows up with some anomalous scaling, which is the core of the discussion that we had done so far. Now, what Krikland was able to show that, in fact, there is a way to show that these equations shows anomalous scaling, that is to say intermittency. And the argument is, roughly speaking, the following. Let's forget about the time derivative, which is anyway very small. So you have a closed equation for this quantity and this quantity. Now, this quantity is not trivial because it includes correlation between the velocity, the temperature difference, and the Laplacians. And the assumption is that you have a finite value of the temperature dissipation in the limit where the diffusivity goes to 0, similar to the velocity. Now you can solve this equation for the second order for n equal to 1, and you can immediately derive what is the scaling law of the second order moment of our velocity difference. The breakthrough of Krikland was to show that, in fact, if you make a reasonable ansatz on this quantity, okay, which is a delicate ansatz, but nevertheless they show that it was a possible answer. In other words, it doesn't violate any realizability condition. Then with this ansatz, you can balance the inertial range dynamics, so the dynamics induced by the advection due to the velocity of the passive scalar with the dissipation, and then you are able to show that the value of the exponent to any power n are linked to the one of the second order by this relation, which is a nonlinear relation satisfying the convexity of the anomalous scaling and showing that anomalous effect are observed even in this linear problem. So there are two basic information in the Kraichner approach. First of all, he recognized that you can pose the problem in a very well-defined way, which is an important statement. And second, he found out that there was a possibility, at least within these ansatz, that anomalous scaling can be observed in this system. Now, the crucial observation for what concerns us is that the anomalous scaling comes from the balance between dissipation and viscous and the transport term. Okay, so it depends on the way in which energy, in this case temperature, is dissipated in the system. Okay. Now, in fact, the answer done by Kraichner was a little bit delicate because it was looking at the limit when d goes to infinity of quantity of this kind. Okay. Now, you remember what I said at the very beginning, that when you go to a very small value of the viscosity, and in this case is diffusivity, then you expect, in this case, a breakthrough, which is actually what can happen in the Kraichner model, of the Lagrangian trajectory. So such a limit, it's extremely delicate. You don't want simply to know the scaling property of this quantity, you really want to know the prefactor in front of it. And in fact, it's much better to consider quantity of correlation of this kind where both small r and large r are within the inertial range, so where no viscosity is acting in the system, where the viscous effects are not yet acting in the system. More generally, of course, what you have to look is the correlation function between the field at different points. And here is where the discovery came through, because when you look at the equation, and I'm now skipping a huge amount of mathematical property, when you look at the equation for this correlation function, then you see that the equations are done by two terms. One, which is due to the transport of the velocity field, this one here, and one which depends on the viscous, on the dissipative effect. Now, Kraichner assumed that these two quantities should be balanced, but you can look at this quantity by itself, and you discover that there are solutions of the equation transport field multiplied by this correlation function equal to 0. These solutions are called zero modes, and the most astonishing result is that the zero modes not only show anomalous scaling, but also dominate the inertial range in the system, regardless of any viscous effect. So what has been observed by this theoretical investigation is that the transport of the system by the turbulence of this scalar field have statistical properties which are intermittent only because of the effect of the transport and are independent on the effect of the way in which fluctuations in the temperature or whatever transport you are considering are dissipated. This was done by a number of people, including Vergata, Gavetsky, Kupianin, Scheiman, Sija, and so on. And after this theory was put forward, there was a non-trivial, very non-trivial effort to perform numerical simulation of the system. And here you see the results for the anomaly, so the part which is anomalous, with respect to the prediction, which are these two lines, which can be computed perturbatively in the case of the Kraichner model. Now, this results confirms that Kraichner balance was not correct, and the most important, that the zero modes were the source of anomalous scaling in the turbulence. Once you achieve the results, then you can show something non-trivial. First of all, not only that the zero modes are dominating the inertial part, I mean what we call the scaling property of turbulence, but also they are independent on the large scale forcing. That is to say, they are independent whether or not you put some anisotropic effect in the system. Eventually, this anisotropic effect, although very slowly, will decrease when you look at very, very small scale, but they have a subleading effect. Okay? You can also predict what was assumed by Kreikner, namely that there is a viscous anomaly. In other words, that in fact, when you multiply the diffusivity by the gradient square of the temperature of the scalar field, then you have something that is independent of the turbulence effect when the Reynolds number goes to infinity. Okay, then you can extend this theory to, at least numerically, but also with some good theoretical approach, with the real passive scalar, because afterwards the Kreikner was dealing with a toy model for passive scalar. And then there are some non-trivial, although minimal, results concerning that the same is true for the Navier-Stokes equations. So the moral of what we understood so far is that, in fact, turbulence, the intermittency or anomalous scaling is built up in the inertial range. Now, if this is true, then when we can do something more, we can take the value of d of h, if you wish. You can take the anomalous exponent observed in the scaling property of turbulence, and then use this information to compute d of h, and use this information to compute the effect of viscosity in the system. In fact, you can start by taking the same approach of Kolmogorov, where the scaling, where the dissipation scale is dictated by the viscosity. This is just the Kolmogorov theory, but now, because the fluctuations of the velocity depends on this h, and we know how the h is related to, is fluctuating in the inertial range at least, then we can compute how the viscous dissipation acts in the system as a function of the Reynolds number. So the first results you observe from this, and that was put forward first by Palladini, Vulpiani, and then by Frisch and Vergasolas, is that in fact the turbulent, I mean the dissipative scale in turbulence is a fluctuating quantity. Once you observe this, then you put everything together, you run a machine of standard algebra, and you can derive two information. One is how the velocity gradient goes like a function of Reynolds, which is non-trivial, and then how to compute the probability distribution of the acceleration, because now it's different from the one predicted by Kolmogorov. It's different because the viscosity enters into the dissipative scale in a way which is dictated by the inertial range dynamics. You remember that I was showing you this line to see that, in fact, Kolmogorov theory was not good, and what can be shown is that if you put the information concerning the anomalous scaling as obtained in the theory from the numerical simulation, then you can predict the acceleration of the Lagrangian particle in an extremely well way. I mean, you see that you have 80 variants at very small scale. You have a factor almost 2 in the acceleration, which has been captured by the theory, while in the Kolmogorov case we have only almost an exponential decay in this region. So that was the first thing that was done, which in fact is an extremely good result. And then the second thing, which is also been done, concerned the prediction that was done actually before, but it's in historical view, the prediction about how the velocity gradients depends on the Reynolds number, And what you are able to show that this prediction is a very good agreement with the numerical and experimental data. And you see here that there is an increase of the relative fluctuation in the viscous dissipation, just due because at the strange and non-trivial effect of dissipations within the anomalous scaling of turbulence. So this is a non-trivial, let's say, prediction, which is validating the approach that we were following so far. But of course, we can do more. And the last results I want to discuss with you concern the fact that by looking at the Lagrangian turbulence, you can really exploit this relation between the effect of transport field, where viscosity is not affecting the system, against the fact that sooner or later viscosity enters the system. So you have a finite size affecting the system. So let's consider the turbulence in the Eulerian frame. The Eulerian frame means that you take 2 points and you look at the fluctuation between 2 points. Now, the smallest scale, eta, where fluctuations occur, goes like Reynolds to the -3/2. So when Reynolds becomes large, this quantity becomes really very small. If you look in time, the same computation, so if you, instead of looking at the velocity in 1 point, you look at the velocity difference between 2 points which are changing in their position in time, then the proper scaling should be derived by looking at the this quantity, which goes like Reynolds to the -1/2. So by looking at this difference, you see that when you look at the turbulence from the point of view of time, you are blowing up, you are increasing the effect of dissipation effect in the statistical property of turbulence. This is in fact what has been can be predicted by the following argument. You take what we know on turbulence, at least experimentally and almost theoretically, in the scaling range. And now you look at the property of the scaling property of turbulence between two Lagrangian particles. So you take, for instance, a velocity particle, you measure the velocity at some time t, and then at some time t plus tau, and then you look at these strange numbers, which is the velocity difference at the time tau. And if scaling is a reasonable assumption within this framework, then you would expect that this quantity should have a scaling law, which is anomalous in P, and these are characterizing the Lagrangian property of turbulence. Now, since you expect that the velocity fluctuation behaves statistically similarly between Lagrangian and Euclidean field, and since the link between R and tau is by dimensional counting something like this, then you can predict what are these numbers if you know what are the Eulerian numbers. And the prediction is a link between this function d of h. Okay? And again, this can be tested numerically and experimentally. There is an uncertainty in the test because, of course, we never achieve an exactly isotropic field. So when P becomes too large, the error bar in measurements are not as good as we should have, but nevertheless, within the error bar, the prediction based on scaling argument is extremely good. Assuming that this is true, then we can look at the anomalous part of the fluctuations deep inside into the viscous regime. So what you take is the second order moment of the velocity difference, and you compare with the fourth order moment of the velocity difference in time. As usual, you see that there is an increase of fluctuation when you go nearby the effect of viscosity. And if you look at the local derivative of S4 to the S2, this quantity A, okay, which is just how the scaling change, you can think of this quantity A as a local measure of anomaly in the system as a function of tau, okay? So in other words, this quantity A is just the quantification of how much strange or strong fluctuations you observe as a function of tau, actually anomalous fluctuations, okay? So when you are in the inertial range for very large tau, you expect something that is the one predicted by the comparison of Lagrangian to Eulerian statistic, and this is this line here. When you are inside, when you go inside the viscous regimes, what you observe is an increase of turbulence, okay? And then when you go at very small tau, then you should recover that the system becomes smooth. And this is in fact what you observe by this green line for particles which are tracer. Now you can put in the system particles which are a density bigger than the one of the fluid, heavy particle, and it's known that heavy particles go outside of the vortices. And what you observe is that, in fact, this dip here is removed. Then you can put particles which are lighter. And what you observe that particles which are lighter and then goes inside the vortex have a much stronger dipper than the tracer. So in other words, this figure is suggesting something that in some sense we already know, but it's even worse than what we know. That is to say that vortices are the one that dominates the viscous fluctuations in these regions. I mean, the intermittency, the anomaly part of the viscous fluctuations in this region. So you can read this figure in two ways. The good way is that, I mean, it's something that we know and is confirmed by this picture. And the other way is that something which put forward, again, the relevance of the formation of vortices into the system and the relevance in the formation of anomalous fluctuation in the system. But before trying to understand what happens really in this system, at least experimentally, okay, let me try to show you what is the prediction of the multifractal theory. Now, this is done in R instead of T, but it's essentially the same results. You see, this is the prediction that you can obtain from the multifractal theory by increasing the Reynolds number. You observe two things, of course. One is that the range where anomalous scaling is observed, the plateau, is decreasing. Okay, I mean it's increasing with the Reynolds number, it's decreasing by decreasing the Reynolds number. And the second thing is that the viscosity, the anomalous fluctuation in the viscous part increase by increasing the Reynolds number. And this prediction is done by assuming to know the scaling property without any information from the viscous effect. So this prediction is telling you two things. First of all, that you have a prediction to compare with the real experiment and the numerical simulations. And the second thing is that when the Reynolds number is extremely low, which is always what happens when you consider, for instance, a flow near an obstacle at very small distance from the obstacle, you may think that the Reynolds number is relatively small, then most of the fluctuations are compatible with the multifractal theory, although they occur nearby the dissipation scale. So this is the reason which confused many people by saying that vortices are dominating the system, for instance, near boundaries. The reason is that they observe fluctuation which comes from the viscous effect, although they are already consistent with the inertial range dynamics. Now, if you now look at the comparison against the real experiment within the error bar that we can estimate both from experiment and from numerical simulation and from the theory, you see that all the data that we've been able to obtain are well within the theoretical prediction. So in other words, what you observe is that vortices obviously are inside the dissipative effect of turbulence. I mean, you cannot have turbulence without vortices, but they have the same scaling property that was from the beginning assumed to be true in the anomalous part of the scaling property of the theory. So in other words, if you look at the transport field in the sense of nonlinear dynamics in the scales where viscosity doesn't play any role, then you have an anomalous part of the system, which is the one to which vortices anyhow should be constrained. So this effort was a clear demonstration about the universality property of the anomalous scaling, both in the inertial part, I mean when viscous effects are not acting, and when viscous effects are acting. So let me try to make a short summary of what we obtained. Of course, we are not yet able to prove that viscous anomalies are observed in the Navier-Stokes equations. In other words, we have no theory for that. I mean, we have good, reasonable, good intuition, but we are not able really to prove that this is the case. We are not yet able to compute d of h. There are cases where we can do something, but essentially we still need a systematic approach. I would say that this problem is really less difficult than the first one, although it is very, very difficult. And this is something which is obviously to be done. But what you obtain is non-trivial. We have a consistent way to describe turbulence from inertial range and the dissipative range. So we have now an approach which so far doesn't present anything which is not observed or verified by numerical and experimental data. We have been able to predict, something, and in particular now we can state that at least to within all the experiment simulation that has been done, all the scaling properties, either with respect to R or with respect to the Reynolds number, are in fact observed in agreement with the same function d of h. In other words, once you know d of h, you know almost all the scaling property of the system, which or quantities which are invariant under the same group of transformations of the Navier-Stokes equation, of course. We have a reasonable good way to estimate finite size effect as any Reynolds number, and by this estimation we can also take information, quantitative information, to measure the anomalous part of the system, and by this we have a reasonable evidence that d of h is universal. And some, not all these results, can be generalized for non-isotropic forcing. So there is something that, we obtain something which I think is rather non-trivial. Why and how can we use the results? Different ways. Of course, there is the possibility to use the result for improvement of numerical scheme in realistic application. This is also linked to recent approach that can be done in the spirit of machine learning. I mean, it's a difficult field, but something can be really done once you know what is the physics behind. We have the possibility to understand from a basic point of view many scientific problems. I will cite only two of them because this is the one I like more, but there are many of them. One is the statistical particle for inertial particles, the statistical property of inertial particles, which is non-trivial because it's important for many geophysical applications and industrial applications. And another interesting point is the turbulent effect in the evolution of population dynamics in the ocean. Another interesting problem where we can now try to understand deeper is to explore similarity or difference for fluid turbulence with different physical property. For instance, we can understand whether in the superfluid turbulence we observe something similar or something different. We can try to really making a good assessment, which to my understanding has not been done yet. In the case of magnetohydrodynamics, we can explore the difference in the case of complex fluids, for instance, fluids with polymers of two-phase flow or whatever. We can tackle the problem of what happens in turbulence in many interesting geophysical flows, like turbulence in stratified mediums, rotating turbulence, thermal convection, and so on. Eventually, by trying to focus on this different kind of turbulence, we may have a good idea to understand how to compute anomalous exponent. I mean, this is just an hopeful idea, but there is no real statement about that. Now, I think that the time is going to be too close. I was giving you some examples, but you can imagine that these examples can the one that I spoke about. And I thank you for your attention for this afternoon. Thank you. Now, so now, if I can answer questions if there are any questions.
Can I make a question, Roberto and Bernardo Spagnolo?
Ah, okay.
Sure, go ahead. I can, or I should write the question? No, the question is, there is, I don't know, there is some connection between anomalous diffusion in turbulence and super diffusion like Lady Fly. There is some, what is the...
Well, I mean, of course, everything is possible, no? In the sense that you can imagine to have a particular kind of flow where such connection can be found. Within the focus I made, I don't think that there is any connection. But this is just within the focus I made. I mean, it's not
Roberto,
a general statement.
Can you turn off your camera?
Ah.
I can record.
Sorry?
So can you turn on your camera?
Well, I did not have any camera, so.
Okay.
Okay. Now,
No,
if you wish, you can see me.
Okay.
Okay.
Can you see me?
Yes. Yes.
Okay, fine. So my statement was that within the framework of homogeneous and isotropic turbulence, the one I was speaking about, I don't see any connection between the Levy flight and anomalous diffusion. Then you can open the world of infinite number of turbulent problem in the system, where definitely you may have such a connection. I'm not aware of it.
Any other questions?
Yes, I have a question for Roberto. So you mentioned that the overall theory
I didn't understand.
Has reached quite an interesting level. You understand me? Do you hear me?
Well, I think that
Roberto,
I hear you from not very well. So can you repeat the question?
Yes. You mentioned that the theoretical achievement allowed to have a clear understanding about the universality of this anomalous scaling law. And what are the following steps in this direction? So, do you need more information from the experimental side, or there will be a further effort on a theoretical ground to better understand this point?
Well, I mean, it's not trivial. There are several things which goes together. Definitely, we need a good idea from the theoretical point of view. We tried a lot of things, and there was no real breakthrough so far. From the point of view of the statistic, from the point of view of experiment and and the numerical simulation, it is definitely true that we need to increase the accuracy, because as you have seen, we still have a large relatively large error bars in some statement, and it is important to achieve definitive conclusions about that. But this is a side point. I mean, the real difference between what has been done for the passive scalar and for the Navier-Stokes equations is that we still need to make an effort theoretically to understand how perturbatively, non-perturbative, whatever, we can have a computation for the anomalous scaling. There are people that pointed out that maybe this is not a relevant point, because I mean, the computation can be a very difficult task theoretically, but you may not learn some new physics out of there. Nevertheless, I mean, this task must be done sooner or later. I think that we have all the information that we must have with the accuracy that we can have now. I mean, if you compare the situations now with respect to 30 years ago, I mean, it's completely different. Now there are many things that has been clearly understood. There are still people that try to make statement now and then about non-universality and other stuff, but I mean, I think that this statement will eventually disappear along the time.
Thank you.
Any other questions?
Just sorry, again another question. There is okay. It is possible to extend your investigation in the case you use stochastic Navier-Stokes equations.
That's a terrible problem. I mean, because you have a major number of troubles in the stochastic Navier-Stokes equation. Anyway, I think that something has already been done in some cases, but at a level very theoretical effort. I mean, not something serious. One thing which looks more interesting, to my understanding, is to look at this. The properties of the Navier-Stokes equation when you change the viscous mechanism. Okay, at least from the numerical point of view, something can be done, and something can also be done experimentally, because, for instance, in two-phase flow or when you have polymer fluids, the viscous property of the system becomes completely different, and therefore an effort in this direction is extremely worthwhile. So if you think in the broader sense, I would say that this is, I mean, a good point to make for the future. Okay?
Mm-hmm. Okay. Grazie. Grazie, Roberto.
Prego. No, of course, being in front of a screen is very difficult to discuss questions.
Yes.
Obviously. Marco, if there are no more questions, I think that we can thank
again Roberto. Yes. Yes.
For this very nice seminar, and we can take ready for the next seminar.
Okay.
Great. Thank you very much.
Okay.
Thank you very much.
Thank you. Thank you.
Thank you. Bye-bye.
Bye.
Thank you, Roberto, for the nice talk. Bye-bye.
Bye.
Ciao Roberto, grazie.
Ciao, grazie.
Ciao Roberto.
Ciao.
Ciao Roberto, grazie.
Grazie a voi. Ciao.
Ciao.
Ciao Roberto, arrivederci.
Ciao, ciao.
Ciao.
Ciao.